Alright, welcome to Mecanum Engine 2, Video 3. So here's the new and improved visualizer. So we've got methods for rendering and showing each of the collision volumes. And we've also got one for showing array, which you've seen in the previous video to visualize the barycentric coordinates. So these are pretty much just setting up variables and submitting commands. Fairly straightforward. So might as well test this terminate function. So in Mecanum Engine at the very end we've got visualizer terminate. Alright. So I've exited and we're calling terminate. Cool. Alrighty, so the color support class. I actually stumbled across a pretty great website that had a bunch of vector colors. So I have a ton at my disposal. So I pretty much had no excuse for only having 3 colors for my terrain because there are a ton here. But yeah, there we go, color class. Okay, so good old PW Math Tools. So when I first created PW Math Tools, I did not catch on for whatever reason that PW stood for periwinkle, and I think it's a little too late to change it now, unless I want to risk ruining my entire project right now and going through and changing PW Math Tools, changing every instance. But anyway, here we go. So we've got all of our intersection functions that I mentioned before. I've got a barycentric 2D function, which I actually don't use in my implementation because it was just sort of this standard function. It worked for me in the past, like I said, but it just wasn't working for me here. Maybe I can use it for something else. I've got a normalize function because I didn't realize that vect.norm was actually normalizing, so I re-implemented it. I've got a linear interpolation function, which I was trying to use with updating the terrain at real time, which I could show you an example of. It's not perfect, but that actually does interpolate. So we've got multiply vectors, add vectors, dot products, getting a projection of a vector onto an OOBB and an ABB. OBB point intersects, which I don't think I used. So we've got intervals, which is using the ABB collision detection, min and max for floats, min and max for vectors, and of course a clamp. So here's the implementation for all of those great math functions. Nothing revolutionary here. Most of the heavy lifting was done when I created these collision volume calculations. And then here's a bunch of other helper functions that I created. Actually, I don't know if they're over there, but yeah, there's a bunch of extra ones for various things that I needed along the way. Cool. Alright, just making sure that I cover everything with the math tool. And onto the terrain, which is quite the beast. Alright. Obviously, I should probably start at the terrain. I should probably find it. Okay, here we go. Let's close all of these. Alright, so first things first, this is the class that sort of creates the terrain model. So most of this code was lifted from the graphics class. So I've got this basic initialize function, which is going to generate the terrain along with its normals and initialize a bunch of cells. So yeah, many days working on that function alone. calculating all these cells, calculating the normals, getting the winding correct. So this recalculate normals function is actually specifically for my randomized terrain implementation. So this is what I'm going to call if I want to, if I want to recalculate the normals, I suppose. But every time I update the vectors, I'm going to have to call this function and redo all the normal math. Yeah. So get back to that later. This is also for my other implementation. This is initializing a sphere and just hooking it up with all the cells, but this does not work because I could not reconcile cells and spheres. Okay. It's an old method. A lot of these are like old methods that I probably should have commented out before showing you. Because, yeah, I don't really need much of an... Okay, here we go. This is something that I actually utilize. So this integrates with the iterator. So what we're doing here is obviously getting a cell at an iterator point. So we're taking the absolute value of I and j, which is going to be our row and column. And then we're multiplying that by the image height minus 1. So that's going to give us an approximation, well, an exact number, an int, rather, out of a float to get that terrain cell. Okay, so you also have a get cell at pos, which is very similar, and it actually utilizes get cell at iterator. So it just turns the position into a row and column value, which we can plug into this one. Okay, this is more iterator stuff. So let's get into the terrain object before we go deeper into that. So what this is doing is keeping track of the actual terrain model. So we've got a terrain pointer, model pointer, a graphics color no texture light. So that was because I wanted to use the vertex shader. So I changed this to color no texture light and found the shader for that. Cool. So let's see. Okay, sorry about that. So terrain object. So I've got a scene entry and a scene exit, which I utilize obviously because this each terrain is like scene level. Cool. So I'm getting into the iterator a little bit here. So this is the actual implementation of the iterator itself. So this is essentially just a bunch of operator overloads. And what these are doing is just sort of interpolating through min and max values of a cell. So we've got our rectangle area class. Yeah, a lot of this stuff is fairly straightforward. We're just sort of interpolating through these values here, which we derive from the actual computation that we were looking at earlier. So we're computing a cell rectangle based on the actual world position of the collidable in question. Yeah, so let's take a look at the more interesting things. Let's find barycentric. Cool, so let's go over this real quick. So in my tank object, what I'm doing to get the barycentric position, obviously every scene has its connected terrain. So in our update, it's got a little convoluted down here. So I'm taking the up vector, and then we're going to change that to scene manager, get current scene, get terrain model, and then calculate barycentric normal based on the position of the ship. So a lot of things going on there. So we've got, first of all, we're getting the scene from the scene manager, getting the terrain object from that scene, getting the model from that terrain object, then calling this function calculate barycentric normals at that specific point. So this is actually highlight cell, which I do not use. I should really start commenting this stuff out. Alright, calculate barycentric normals at this point. So we're going to be using the iterator to get a cell at this position. And then we're going to use that cell as part of our calculation here. So, this is where I'm checking the actual triangles of that cell. So if the x position of the cell, so we're in cell space here, so we're taking a percentage which is based on the 0, 0 position of the cell and the 1, 1 position of the cell. So my winding is, I don't know really how to describe it. The 0, 0 position is in the top left, 1, 1 position is in the bottom right. So this is just sort of schlepping it into that space. The barycentric calculation is using these values as a percentage, basically, to interpolate between the top left normal, the top right normal, and the bottom right normal. And then obviously we have our nice visualizer, I still can't say it here, to show the array at a specific location. So actually what I'm doing here is pretty much just keeping the pverts and the cell around, so I'm not deleting them immediately. And this is really useful, especially when I'm working with the colors, because there's already an RGB value inside of pverts, and there are dedicated values for the normals. So I didn't really see a reason to throw them out immediately and store the normals somewhere else, because it was all sort of nicely encapsulated in this data type. So that's what I'm using for the actual barycentric calculation. So these are the normals, and I also have calculate barycentric position, which does pretty much exactly the same thing, except we're getting the position from these verts rather than the normals. So if we go into vertex stride VUN, so right now I'm actually just getting the XYZ value of the verts, and up here, if you look, we're getting the normal values, which were set all the way up here. Alright, so pverts, NX, NY, NZ, and then we've got the top left, top right, bottom right in these cells. So the cells hold integer values that I utilize with the pverts variable to grab specific normals and points for the barycentric calculation. So that's how all that works. Oh geez, this is a very long file full of functions that I don't use, so I'm very sorry that I have to scroll through all this stuff. Okay. Yeah, so the position works pretty much exactly the same way, except we're not showing rays. We are showing rays? We are showing rays. Okay, cool. No, we're not. Great. Okay, that about does it for the terrain model itself. Okay, so how we manage terrain. Let's go over to the asset manager for terrain. Alright, so I've got its own dedicated manager and attorney, so we can delete it when we're done with it. So this is actually, the default path for this is actually going to come through textures, because the TGA is what we care about in terms of when we're loading the terrain itself. So if we take a look at our main engine thing here. So we're loading in a terrain. We've got a terrain object manager, load terrain, give it a key, and then we pass in the TGA. So these are all the values that we're going to be using for actually loading the terrain model, so the user never touches any of that. Well, they do when they initialize it, but they don't have to touch it at runtime. Okay. Yeah, pretty self-explanatory. It works just like every other manager here. And of course, this is all at the scene level. So if we take a look at one of our scenes, scene demo. All right, all we have to do is call set terrain, and then pass in the key for the terrain that we already loaded. And we should be good to go. There's no other overhead here. Of course, if you want to detect collision between an object and the terrain, you're going to have to submit collision for that, but that's all you really need to do. Cool. Just checking this document to make sure that I pretty much have everything down here. Terrain normals, terrain manager, collision with terrain. Okay. Yeah, so I can go over the collision with terrain. I think that's the only thing that I really didn't touch on yet. So we do have a command for terrain collision. Sorry, this is getting very convoluted. Collision test terrain. This is the one that I want. Okay, cool. So this is what's going to be called every time that we actually collide with the terrain. And you saw it working, so you can step through here. So essentially this uses the iterator that we mentioned before. So we were grabbing our candidate cells just like you told us to in the slides pretty much. So the candidate cells are going to be a rectangle area that's based on the default B-sphere of whatever's colliding with the terrain. So when we calculate that area, that's what we're taking into account. Compute cell rectangle, so we're getting the B-sphere, the midpoint, and then this is very similar to the way that we're going to calculate the group ABB. So we're just getting the min and max point of the default B-sphere, and then setting it up to be the area for the candidate cells. And then we're taking the actual B-sphere and detecting collision with that. And finally, we are calling intersect on whatever the collision volume of the guy in question is. Yeah. So that's how that command works. Yeah, fairly self-explanatory. So it's just like every other collision command. We set it up in the scene level there, and you saw it working many times. So you saw the iterator, and obviously if you want to see much more of that, you can step through. Cool. Alright. I think that is about it for the terrain. So I'm probably going to call this video quits. Let me just look through this this document real quick. Okay, cool. Yeah, then we should be good. Just mentioning real quick that we do have sort of a tiered ABB B-sphere collision going on with test terrain command, because you mentioned that in the document here. Alright, sorry for the very long video. That concludes video 3.